All right, we're picking up on Chapter 14, the Zumdahl textbook, with our AP Chemistry students, and we have already done the first installation of these notes with 14.1 through 14.3. Remember, we finished off with pH, talking about the pH scale and how to calculate it. So this set of notes, 14.4 through I believe it's 14.5, is going to be on calculating pH for both strong and weak acid solutions. So the approach for calculating pH for a strong acid solution is a little different than the approach for a weak acid solution. So it's important to remember the strong acids. Remember, the strong acids were listed back here somewhere. Where did we list them? Here they are. Hydrochloric, hydrobromic, hydroiodic, chloric, perchloric, nitric, and sulfuric. Remember that these acids are always treated as strong, and so you calculate their pH a little differently than acids such as these, which are weak. Their ionizations or dissociations are only partial before they reach equilibrium. So let's start with calculating pH for strong acid solutions. Now, with any of these problems where they ask you to find a pH, you want to first identify your major species in the mixture. So I'm going to be demonstrating that on each example problem that we do. Let's say that we have an example where we're supposed to find the pH of a 1.0 molar solution of HCl. First thing you want to do, identify your major species. So it's an aqueous solution, so we know there's a lot of water available, and we know that water does undergo autoionization to form H+, so it is possible that water might be a source of H+ here. Of course, the Kw for the autoionization of water is only 1 × 10⁻14 at 25 Celsius, so water is not a huge contributor of H+. Solution also contains HCl. Since it is a strong acid, we are going to assume that its equilibrium lies far to the right. So notice here I'm only going to write the arrow to the right for HCl because it forms H+ and Cl- to a very large degree, nearly 100% ionized in water. So we'll just say here the Ka is very large, much greater than 1. So obviously it looks here like H+ in the solution is going to be supplied by the HCl. I think we can neglect any H+ supplied by the water, especially since the H+ from the HCl is going to push the equilibrium for the water back to the left because you're adding a product H+. So we're going to assume that the ionization of the water is very minimal and that all your H+ comes from the ionization of HCl. So now the question is, how much H+ do we have? Well, HCl is 1 molar, 1 mole for every liter. Each HCl molecule forms 1 H+, so that's a 1-to-1 mole ratio between the HCl and the H+. So we can assume here that the H+ in 1 molar HCl is 1.0 molar. So now it just comes down to finding the pH as the negative log of the molarity of the H+. So the negative log of 1 is 0. Or we could say the pH here is 0.00. The 0.00 showing 2 sig figs in the molarity of HCl. 1.0 molar has 2 sig figs. So remember for pHs that it's only the numbers after the decimal that are considered sig figs. Okay, a couple examples of finding the pH of some strong acid solutions. First, a 0.10 molar HNO3, and then a very dilute 1.0 × 10⁻10 molar HCl. Starting with the HNO3, our major species are going to be water, H+, and NO3-, because the HNO3 will be split into ions. because HNO3 is one of our strong acids. Water is going to be a minor player here. If you consider NO3 minus, you might say, well, wait a minute, NO3 minus, that's a conjugate base. It's a conjugate base of HNO3 That might affect the pH. But remember, HNO3 is a strong acid, and the stronger the acid, the weaker its conjugate base. So since HNO3 is considered to be completely strong, we consider NO3 minus to have no effect on the pH. So the pH is going to be determined by the H plus that you get from the ionization of HNO3. So HNO3 makes H plus NO3 minus. The molarity of the HNO3 is the molarity of H plus, since it's a 1-to-1 ratio. So H plus's molarity is 0.10 molar. pH is going to be the negative log of that, which is 1.00. So 0.1 molar HNO3 has a pH of 1.00. Now let's try to find the pH of the second half of the problem, which is 1 times 10 minus 10 molar HCl. So our major species here are water and H plus from the HCl and Cl minus from the HCl. Now we've already talked about the Cl minus. We can neglect that because HCl is a strong acid, so Cl minus is going to be a completely weak base that's not going to have any effect on the pH. So now we look at the H plus and the water as the two major contributors of H plus. Remember, the autoionization of water contributes 1 times 10 to the minus 7 molar H plus, but the complete ionization of the HCl is only going to contribute 1 times 10 to the minus 10 molar H plus. That's 1,000 times less than the H plus from water. So I think we can pretty much assume here that the molarity of the HCl is so low, its concentration is so low, that it doesn't contribute enough H plus to the water to even change its pH. The pH is going to be the H plus from the water, or 7.00. Now, we take a much different approach when we try to find the pH of weak acid solutions. Weak acids have equilibrium reactions when they dissolve in water, which means we have to treat them as equilibrium problems, not as stoichiometry problems like maybe you could treat a strong acid, where we just use the mole ratio. To illustrate this, let's try to find the pH of 1 molar HF. HF has a Ka value of 7.2 times 10 to the minus 4. So our major species here are going to be H2O, H plus, F minus, and I kind of left one out here. Let me see if I can escape and put it back in there. I probably should have included HF as a major contributor, or at least a major species. May not be a contributor, but it's a major species in the water, that you have some water molecules, you have some HF molecules that are not ionized, you have some H pluses and F minuses, which are the HF molecules that are ionized. So important here that we recognize that we have both the unionized acid and the ionized ions from the acid. So looking at our two K values, the H plus from the HF comes from a Ka value of 7.2 times 10 to the minus 4. The H plus from water comes from a K that's only 10 to the minus 14. So again, just like with strong acids, it looks like we can assume that the weak acid is the major contributor of H plus here. HF is the primary producer of H plus. However, we cannot assume that the 1 molar HF is now 1 molar H plus and 1 molar F minus. It is a weak acid, which means it's only partially ionized at equilibrium, so we need to make an ice table. So here's my ice table. HF makes H plus plus F minus. The initial molarity before the reaction shifts to the right to reach equilibrium is 1 molar HF, and 0 for the H plus and F minus. The change is going to be that the HF is going to go down by X, the H plus and the F minus are going to go up by X, giving us an equilibrium value of 1 minus X for the HF X for the H plus, and X for the F minus. Now plugging that into the equilibrium Ka expression, we get Ka equals 7.2 times 10 minus 4 equals X squared over 1 minus X. Now this is one where I can take the shortcut. 1 minus X is approximately 1.00 because the Ka is small. So that's going to save me some quadratic equation solving. X is just going to be the square root of 7.2 times 10 minus 4, which is 2.7 times 10 minus 2. That does obey the 5% rule, because 2.7 times 10 minus 2 is only 2.7% of 1.00. So that means we are now finding the pH by taking the negative log of the H plus, which is X, so that's negative log of 0.027. So your pH would be 1.57. All right, so that showed us how to find the pH of a weak acid by setting up an ice table and solving for X. What if we had a mixture of weak acids? Usually these problems are done where one acid is noticeably weaker than the other. For example, find the pH of 1 molar HCN with a Ka of only 6.2 times 10 minus 10 and 5 molar HNO2 with a Ka of 4 times 10 minus 4. Now, to add an extra dimension to this problem, they also ask us to calculate the concentration of the cyanide ion in the solution. So our major species are H2O, H plus, the unionized HCN molecule, the cyanide ion from the ionization of HCN, the HNO2 molecule that is unionized, and the nitrite ion from the ionization of HNO2. So it's quite a mixture there of ions. But I think if we compare our Kas, the HNO2 is not only 5 times the molarity of HCN, it's also nearly 10 to the 10th greater in Ka value. So I think it's pretty clear here that our H plus is mainly going to come from the HNO2. So setting up an ice table for HNO2 using 5.0 as the initial molarity of HNO2 and then doing the old 0, 0 minus X plus X plus X, 5 minus X, X and X, and then solving for X using the Ka value of 4 times 10 to the minus 4. Also taking the shortcut, 5 minus X is approximately 5. I find that X is the square root of 5 times 4 times 10 minus 4, which is 2 times 10 minus 3. So I get square root of 2 times 10 minus 3, which is 4.5 times 10 minus 2 molar. Now this is only 0.9% of 5, so we have a good approximation. So our pH, which is the first half of this question, is going to be the negative log of the H plus ion molarity, 4.5 times 10 minus 2. We actually have a pH here of 1.35, which is pretty acidic. Now the second half of the question said calculate the concentration of the cyanide ion in this solution. Well, obviously I can't get the cyanide ion from the HNO2 reaction. To get the cyanide ion, I have to consider the equilibrium of HCN in water. HCN in water forms H plus plus Cn minus. My initial HCN molarity is 1.00 molar. Now you might think, and this would be your mistake, would be putting 0 in for H plus. But remember, there's quite a bit of H plus available from the HNO2. There's 0.045 molar H plus available from the HNO2. That was our number calculated in the previous half of the question. So that H plus is going to be present also in the HCN equilibrium because these are all in the same solution. So I have to assume an initial molarity of H plus of 0.045 molar. I can't assume it's 0 because we are in an acidic solution with 5 molar HNO2 that has a pH of 1.35. So we can't just start out our H plus and say it's 0 because it's not. It's 0.045 molar. However, before the equilibrium is reached here, we can assume Cn minus is still 0 because we haven't shifted to the right at all. So as we shift to the right, we get minus x, and plus x, or 1 minus x, 0.045 plus x, and x. Solving for x in the Ka expression, we get 6.2 times 10 minus 10. The Ka for HCN is 0.045 plus x times x over 1 minus x. Here we're going to not only drop the minus x from the bottom, we're also going to drop the plus x from the top and simplify this down to, on the right side, to 0.045x over 1, which makes this a much easier algebra problem. X is 1.4 times 10 to the minus 8 molar. And X, if you recall from the ice table, is the molarity of Cn minus cyanide ion that we were looking for. Now this does work because it passes the 5% rule for both the 0.045 and the 1.00, and this degree of 1.4 times 10 minus 8 molar, that actually makes more x, or at plus x for the H plus, that's going to be negligible in comparison to the 4.5 times 10 minus 2 molar that we saw from the HNO2. So the plus x here does not add anything to the pH of the solution. And we passed the 5% rule, so we've solved both halves of that problem. Now sometimes instead of describing things as pH, there's also an approach where you talk about percent dissociation, or I would prefer the term percent ionization of a weak acid. So to kind of throw this math into the mix along with pH, so instead of just saying what is the pH of the solution, what is the percent dissociation? Is it 1% dissociated? Is it 10% dissociated? Remember, when we talk about weak acids, we often say, you know, the percent dissociation is very low. Let's practice on acetic acid, Ka 1.8 times 10 minus 5th at 25 Celsius. Let's do some 1 molar acetic acid and find its percent dissociation. Setting up an ice table for it, just like the previous Ka ice tables that we've done. We get 1 minus x for the acetic acid at equilibrium, x and x. We throw those into the Ka expression. 1.8 times 10 minus 5 equals x squared over 1 minus x. We neglect the x on the bottom. X squared now equals the 1.8 times 10 minus 5th. Take square root of that. X equals 4.2 times 10 minus 3, which is only 0.42% of 1.00, so it passes the 5% rule. Now, to finish the question, the percent dissociation is going to be the amount that we are subtracting from the 1.0 divided by the 1.0. So out of that 1.0 moles per liter of acetic acid molecules, how many of them are dissociated? The number is x, and x is 4.2 times 10 minus 3. So that divided by 1 then times 100 is 0.42% dissociation, or ionization, I would prefer. Now to compare that 0.42% to 0.1 molar acetic acid, so now I'm doing part B, 0.1 molar acetic acid. I just took the previous problem and did a bunch of substitutions, 0.1 for 1.0. So now we're calculating it for 1/10 molar acetic acid. Going through all the same math with it, we find that x is 1.3 times 10 minus 3 molar, which works out to be 1.3% dissociation. Now that does pass the 5% rule, but this 1.3% is greater than the 0.42% that we saw in the previous solution. So the 1/10 molar acetic acid is more dissociated than the 1 molar acetic acid, at least as in terms of percent dissociation. It does have a lower molarity. 1.3 times 10 minus 3 molar H plus is less than 4.2 times 10 minus 3. So we have less H plus in the diluted solution, but we have a higher percent dissociation. So here's where you could go back and plug in your Le Chatelier's principle to it. You added water to an equilibrium that had one molecule on the left and two ions on the right. By increasing the volume, just like with gases, increasing the volume, you're going to shift in the direction that has more species. So diluting increases the volume, and you shift in the direction of the right, which has two ions instead of one molecule. Going the other direction, because remember with AP Chemistry you want to learn how to work problems forwards and backwards. Often the problem you learn in class going forwards gets asked on the AP test working it backwards, because they like to see if you really understand the problem solving, not just memorizing a technique. So let's find the Ka from a percent ionization. We'll go with lactic acid here, and let's say we know that it is 3.7% dissociated when it's in a 0.100 molar solution. And we just showed on the previous problem that the molarity does matter. So we do care what the molarity is when we solve these problems, because different molarities have different percent dissociation. So we're finding Ka. So I've set up my ICE table with this lactic acid's formula here, making H plus and lactate, minus X plus X and plus X and 0.1 minus X, X and X. So we know that the X is 3.7% dissociation compared to 0.100. 3.7% of 0.1 is 0.0037. So our Ka is X squared over 0.1 minus X. Plugging in 0.0037 for X, we get a Ka of 1.4 times 10 to the minus 4. So just to summarize here, 14.4 and 14.5 here, when you're working these acids, and also as we're going to see in the next section, base equilibrium problems, the first step is, what are your major species? Are there any the second step, are there any reactions we can assume go to completion, like a strong acid? Can we assume that certain reactions go to completion? If not, then what is the equilibrium that's going to dominate the solution? Which equilibrium has a greater K value? That's typically going to be the one that's going to give you the most ions. And once we figured out what equilibrium is going to dominate, we set up our ICE table and we solve for our equilibrium concentrations from the K values, the Ka values or so forth, that they give in the problem. Then we check for any simplifying assumptions like 5% rule, and then we solve for things like this is the final pH, or this is the final percent dissociation, or this is the molarity of cyanide, as we did in one of these problems. Okay, so I'm going to wrap that up here, and I will try to finish up the rest of the chapter sometime in the next few days. Remember, our quiz is not until next Friday, February 12th.